Welcome back. With this video, we will finish up Chapter 16. And at this point, we are up to discussing the electric field. After we do that, we'll talk a bit about field lines, electric fields in conductors and non-conductors, and then depending on the time, we will talk a bit about DNA. We'll start with the electric field. The electric force is a force acting at a distance. So I've traded out my frogs for Daleks. So let's say these are two charges. Let's say they're positive in red, negative in blue. They don't have to be in contact in order to have a force between them. You have a positive charge here and a negative charge here. We can use Coulomb's law to figure out the force of attraction or repulsion, and there's some distance between them. So that's what we mean by electric force, is a force acting at a distance. And it's like gravity. We don't have to be in the center of the Earth to feel the gravitational pull of the Earth, for instance. It's helpful when we think about electric forces to also think about electric field. Just like with gravity, we can think about a gravitational field. All right, for an electric field, it extends outward from every charge and permeates all of space, although its magnitude decreases as 1 over r squared. We can map out a field by considering a test charge. So let's look at that. If this is our charge, this Dalek, and so we give it a charge plus q, then we can take a test charge and we can move it as shown in this picture from A to B to C. If you read the textbook, it goes through this. It doesn't make it really clear that test charge has to be positive, but that's critical. It's there, but it's kind of buried. Let's make the little ladybugs so they're both red, so they look the same, they're both positive charges. We'll make the red ladybug the test charge. So here's our charge plus Q, and we want to figure out the force acting on the test charge as we move it around that positive charge. So if we put it at A, the force acting on the ladybug is away because they're both positive, so they repel. So the force on this is away from this main charge. And if it's pretty close, it has a pretty strong force, so the arrow is pretty long. We move it over to B, which should be this direction, I think, as you're looking. Then the direction of the force is going to still be away from our main charge, but we're a little farther away, so the arrow is a little shorter. We move it over to C, even a bit further away. Then the direction of the force is still away from the main charge, but it's even further away, so the length of the arrow is even a little bit shorter. So figuring out all these forces just follows Coulomb's law, which is given in the upper right of your screen, that K Q1 Q2 over r squared. All right, that's review. That's a review of Coulomb's law. But if we think about the strength of that, the force on this charge, we can use that to map out the electric field. And that's what's done in this diagram. You've got your charge there in the center, and those lines are showing you electric field lines from that charge. And if it's a positive charge, electric field lines will be radially outward. You can make a couple observations here that I'll repeat later, and that is that those electric field lines go radially outward from your charge. They don't cross each other. They meet on the surface of the charge, but they don't cross each other. And the strength of the electric field is going to be proportional to the density of those field lines. So when you take a test charge and bring it close to your main charge, the force is strong there. Your electric field is strong there, and those electric field lines are closer together. You move it farther away, it's like the spokes on a tire. Your electric field lines are now farther apart out here, and your electric field is weaker out here. And the force on a charge out here would also be weaker. Okay. We can quantify that electric field. And if we do it in terms of that little test charge, and we'll call the little test charge, that ladybug charge, a lowercase q, the strength of the electric field is the force that little test charge experiences divided by the magnitude of the charge, little q. Little q just tells you it's a small test charge. It's still a charge. It's not really different from this being a large charge, just to designate it's a small test charge. So little q, big Q are both charges. So you can see one way of representing electric field is it has units of Newton per Coulomb, because our units of force are Newtons, and our units for charge are Coulombs. So our electric field has units of Newtons per Coulomb. All right, now let's take it a little bit farther. If electric field is force per charge, and force we can get by Coulomb's law, K, Q1, Q2 over R squared, and Q1 and Q2 are the little test charge, little q, and the main charge that's under examination, our big Q, and all of that is divided by that little q, that little test charge, then the little q's cancel, and we get K, Q over R squared. And that's what's written here. So this is another way to quantify the electric field at a point. And it's generally more useful because we don't need a test charge anymore. The test charge dropped out. So the electric field at any point equals K, that same proportionality constant, times Q, now that's the charge of interest that's being studied, our example, the red Dalek, that was the center. And then R is your radial distance away from Q. So electric field is inversely proportional to distance squared. So it falls off. And that's actually what we could see visually with those spokes going outward, that when you got further away, it fell off. And not just linearly, it fell off as the effect of going radially, having those spokes go radially outward is having the electric field fall off, not just as R, a radial distance, but as R squared. All right, we can also write that in terms of that permittivity of free space again, because K equals 1 over 4 pi epsilon 0. I don't tend to use this form, but I have it here again for completeness. All right, so electric field can be understood quantitatively as K, Q, the strength of that charge we're looking at, divided by R squared, the radial distance from the charge. Okay. So this is a review that we had in the previous slide. Electric field is force per charge. So if we are given the electric field at any point in space, we can calculate the force on any charge Q placed on that point. So we can rearrange and solve this for force. So force, we just rearrange this as the electric field times Q, our little test charge. So as shown on the right, if this is our electric field, this red arrow pointing up to the right, if we drop a positive charge, like our positive test charge in our example, into that field, it'll experience a force in the direction of the electric field. That's what we saw before it was how we created our electric field. We moved that test charge around and it experienced a force radially outward, and the test charge was positive, so a positive charge has a force in the direction of the electric field. And its magnitude can be figured out as just the strength of the electric field times Q, the amount of the test charge. Now, if you drop a negative charge in that electric field, let's go to, this should show up well. It's not very exciting, but this little green piece of plastic. You could imagine you had your little charge here, and if your test charge had been a negative charge, then the two would have attracted, and the direction of the force would have always been inward. But we've already defined our electric field as going radially outward from here. So a negative charge will have a direction opposite of the electric field. So you can think about that a bit. The takeaway message is you drop a positive charge in electric field, the force is in the direction of electric field. You drop a negative charge in electric field, the direction of force is in a direction opposite the electric field. Another useful way to think about this is electric field lines go from positive to negative. And since opposites attract and likes repel, if the electric field is going from positive to negative, you can imagine a negative charge up here. The positive charge would be attracted to it. In contrast, if you had a negative charge here, and the electric field is going from positive to negative, and there's a negative charge up here, the negative charge would be repelled by it. So it's in the opposite direction of the electric field. Okay, I think that covers that idea. So just as we had superposition of forces, if we had several charges in a line, we could, let's say we had 3 charges in a line, we could figure out the net force on one of them by figuring out, say, let's find the net force on the ladybug. We could figure out the force of the blue Dalek on the ladybug, the force of the red Dalek on the ladybug, and then we add those 2 forces and we get the net force on the ladybug. So we've done that. You can also do that for electric fields. If you wanted to figure out the strength of the electric field at some point, and there are many charges around, you could figure out the electric field from one charge, add to that the electric field from another, and a third charge, and so on, and you can get then the net electric field at that location. Okay. So, problem solving with forces and electric fields. First, draw a diagram. That's very helpful. Show the charges. Make sure you show whether it's a positive charge or a negative charge. And it's often helpful to draw electric fields. So they'll go radially outward from positive charges and radially inward to negative charges, and they'll go from positive to negative. And we'll go over that a bit more in a second. So get your electric fields with forces and directions. Calculate the magnitude of the force with Coulomb's law. Get the direction of the force by considering the signs on the charges. So opposites attract, like charges repel. And then add those forces vectorially to get a result. And for the purposes of exams in this class, our charges will always be on a line, so you're just doing vector addition or subtraction, but you still have to figure out the direction of those vectors to know whether to add or subtract them. All right, so let's look a bit more at those field lines and give images to what I said in the last slide. So electric field can be represented by field lines. Field lines start on positive charges and end on negative charges. So if you have a lone positive charge here, the electric field lines go radially outward. That's just the example we started with. If we have a negative charge, we again have a radial pattern, but the electric field lines go from positive to negative. So they come in towards a negative charge. So same pattern, but the field lines now point radially inward. Okay, number of field lines starting on a positive charge or ending on a negative charge is proportional to the magnitude of the charge. So visually you can see if you have more charged particles, you'll have more electric field lines. And the electric field is stronger where the field lines are closer. So when you're close to a charge, those field lines are closer together, the field is stronger. Go further away from a charge, and the field lines are farther apart, and the field is weaker. All right, a couple other images of electric field lines. If you have, we call an electric dipole, one positive charge and one negative charge, equal amount of charge, the electric field lines go from positive to negative. If you're right on the line between them, it's a straight line. Otherwise, they curve around from positive to negative. Some of the field lines go out into space here on the far side, but on the side facing the other charge, they go from positive to negative. The direction of the electric field at any point is a tangent to that electric field line. So at this point, the tangent to that electric field line is up here to the right, a bit steeper than the electric field line itself. If you need a review of what a tangent is, you can think about a circle with a radius. And if you draw the radius to a circle, perpendicular to that is your tangent line, perpendicular to that radius. Okay. Another example, two positive charges and how their electric fields interact. I mentioned before electric field lines never cross, so they go radially outward from this positive charge and the field lines go radially outward from this positive charge, but those field lines aren't going to cross, so they start to approach each other, but then they tangentially disappear off our screen here, and that's our pattern for two positive charges. Two negative charges, it would look the same, just the direction of the field lines would be opposite. They'd be going inward towards the negative charges. All right, if you have an unequal distribution of charge, let's say you have a negative charge here, but you have a positive charge with twice as much charge here, this shows you the relative density of the field lines. Field lines still go from positive to negative, but because there's twice as much charge here, we have twice as many field lines emanating here. So there's 6 field lines coming in here, 12 field lines emanating out of our positive charge there. Okay. One thing you can notice, these charges are all, you can consider them conductors, and they always intersect the surface of the charge perpendicular. So if you have a conductor, the electric field lines will always come in perpendicular. We'll actually see that again in a minute, but you can see it here as well. All right, give another example for field lines. Let's consider two parallel plates, and we'll consider this again in upcoming chapters. Two parallel plates of opposite charge is actually a capacitor. So if you have a positively charged plate here and a negatively charged plate here, the electric field lines shown in red go from positive to negative, and you get a nice uniform electric field between the two plates. So they aren't getting farther apart or closer together. That's what we mean by a uniform electric field. The field lines are all parallel to each other. That means the electric field is going to have the same value throughout here because they're all evenly distributed, the field lines here. Okay, at the edges we can get edge effects where the field lines bow outward slightly at the edges of these conducting plates. Okay, so summary. Field lines indicate the direction of the field. Field at any point is tangent to the electric field line. The magnitude of the field is proportional to the density of the field lines. Closer to a charge, the field lines will be closer together, the field is stronger. Further out, the field lines are farther apart and the field is weaker. Field lines start on positive charges and end on negative charges, and the number of field lines is proportional to the magnitude of the charge. All right. What about if you have a conducting material? So section 16.9 is electric fields and conductors. So here we have a conductor, and there's a positive charged object inside it. So you can think of this as, say, a metal washer. And somehow we've placed some positive charge inside there. What happens in the conductor? If we have a static electric field, and that's all we deal with in chapter 16, we don't have currents yet, where charge is moving. If we have a static electric field, inside this conductor itself, inside this gray area, inside this metal washer, the static electric field is going to always be zero inside a conductor. If it weren't, if there were a net field here, this is a conductor. Electrons are free to move in a conductor. The electrons would move under the influence of the field. They'd move in the direction opposite the field. And they'd move until they couldn't move anymore, and then they'd get to their stable orientation. So, if you move this charge around, then you could get some motion of charge within the conductor. But when things are static, if this charge is not moving and static, then there's no field inside the conductor. But what do you see here? The electric field in this positive charge goes radially outward. And what happens in a conductor? Electrons are free to move. The electrons are attracted to that positive charge. So all the electrons are lined up on the inside of our washer. That leaves you with an excess of positive charge on the outside. And the way I find it easiest to think about is that the electric field from this positive charge is going radially outward, but the conductor has its own electric field that goes in the opposite direction from positive to negative, from the outside to inside, and those two fields cancel each other. And the net effect is no electric field inside the conductor. That's your bottom line. That's what you want to remember. Inside a conductor, under static conditions, there's no electric field. However, because all the electrons lined up on the inside of our washer here, and we got a net positive charge on the outside, then that net positive charge is a source for an electric field that continues beyond the conductor as if the conductor were not even there. And that's what you see in that image. Okay. Net charge of conductor is on its surface. You have net negative charge on the inside here and net positive charge on the outside. All right. So the electric field for any conductor is going to be perpendicular to its surface. If it weren't, let's say you had an electric field at some angle, so there was some portion of electric field parallel to the surface and some portion of the field perpendicular, well, the electrons would move. They'd experience this force parallel to the surface. The electrons would move in the opposite direction until they got to their static orientation. Then the electric field would be perpendicular to the conductor. So if it weren't perpendicular, charges would move. Under static conditions, things come to equilibrium, and the electric field is always perpendicular to the surface of a conductor. If your lab this year is similar to past years, this section will be very helpful for you. Make sure if you have conductors in your lab experiments that your electric field lines always come into the conductor perpendicular. Make sure if you happen to have an experiment where you have two parallel plates, you'll see at the edges of the plates the electric field lines have an edge effect where they bow outward, but otherwise in between the two plates there's a uniform electric field. The field lines just go from positive to negative. Okay. What about a non-conductor? Rather than having a metal washer, let's say you had a wooden piece of wood there. Well, in the wood, the electrons aren't free to move, so you can have an electric field pass through a non-conductor because the electrons won't move and rearrange themselves. So there can be an electric field in a non-conductor. And in addition, the electric field doesn't have to be perpendicular to the surface of a non-conductor. If you have some piece of wood and the electric field is going through it, no electrons are moving can move it in response to that. They're locked in their atoms within your non-conductor. The electric field does not have to be perpendicular to the surface of a non-conductor. All right. Well, I'm already at about 23 minutes, so I'm going to skim through these. I like to have the videos between 20 and 30 minutes long. So for those with you with a biological interest, I would say spend a little bit more time here. I'll quickly comment that within DNA you have your AT and GC nucleotide bases, and they attract each other through electrostatic forces. So there's a nice biological application for these sort of electrostatics. And in duplication, if you have sort of a DNA soup with all these radionuclides floating around in there, A and T will be attracted to each other, and G and C will be attracted to each other, and other combinations are not. So that helps with DNA replication, electrostatic attraction. Okay. Finishing up, just as a little review, let's think about if you have a uniform electric field, let's say here, uniform electric field to the right, what happens if you release a charge in that uniform electric field? So let's say you have a uniform electric field to the, I guess I'm opposite. So if it's to the right, and then you release a charge in there, a positive charge, what happens to it? It will move in the direction of the field lines. A negative charge, if it's released in there, will move in the opposite direction of the field lines. Or you could say it experiences a force in one direction or the other, and if it's free to move, it will move in that direction. Okay, that finishes up chapter 16. I guess I'll go through a quick review. There are two types of electric charge, positive and negative. Opposites will attract, so a positive and negative charges will attract each other, while likes repel. Two positive charges will repel each other, two negative charges will repel each other. Charge is conserved, so if you get extra electrons in one place, you'll have a deficit somewhere else. The charge on an electron is 1.602 times 10 to the minus 19 coulombs, and that is a quantized amount. We can't subdivide that anymore. All charge comes in multiples of the charge on one electron, or that's equal to the charge on one proton, except for an electron it's negative, for a proton it's positive. I've thrown in the mass of an electron there as well, just for reference. In a conductor, the electrons are free to move from one atom to another. In insulators and non-conductors, the electrons do not readily move from the atom. There we have again, charge is quantized. Objects can be charged by conduction or induction. In conduction, two objects touch and charge is transferred. In induction, it's a little more complicated. You bring a charged object nearby. You have nearby, say, your neutral object is connected to ground. The nearby object causes charge to move. You disconnect the ground, and now and you can remove your charged object, and you're left with a charged object here. That's induction. You can go back and review it in the first video. Coulomb's law. The force that that two charges exert on each other is K, that constant, 9 times 10 to the 9 Newton meter squared per Coulomb squared. The product of the two charges divided by the distance between the two charges squared. Electric field is force per unit charge, so you can write it as E equals F over Q. Or for a point charge, Q, the electric field is KQ over R squared, and we're able to derive that fairly readily. Electric field can be represented by electric field lines. Field lines go radially outward from positive charges, inward to negative charges, and if you have a positive and negative charge, they go from positive to negative. And where we finished up, the static electric field inside any conductor is 0. On the surface of the conductor, the field is perpendicular to the surface. but you can have a static electric field inside a non-conductor, and the surface field does not have to be perpendicular to the surface. All right, that's it for chapter 16, and I'll see you soon with chapter 17.